Hi everyone, my name is Adrian Rhem. I'm a PhD student here at Laurentian into my second year with the Gold Fluid Window Project. And today is my first presentation for the partners meeting. So I think I would give an introduction to my project and go over some of the main concepts here, which is essentially looking at the Syn-Metamorphic Gold and fluid mobility in the Poetico Subprovince, the Quantitative PTTx approach. And as Antoine mentioned, this is a collaborative project with the Harquail School of Earth Sciences and Université Laval. And so I'm going to introduce the concept a bit more, dive into the gold fluid window concept a bit more, as well as metamorphic devolatilization model, and then talk about the geologic setting, the Poetico subprovince, why it's an important area. Also, I'm going to try and outline the objectives and the the PTTx approach, and then we'll focus on the results from fieldwork and from transect mapping from the last 2 summers. And then a couple slides, I'll present some preliminary results and interpretations from petrography and phase equilibrium modeling. So as many of you are aware, the Archean orogenic gold deposits are often situated along subprovince boundaries that separate the metasedimentary and metavolcanic or greenstone belts. And so we have two main lithologies that we want to consider there for the gold sourcing. The source processes that lead to the gold deposition are currently highly debated. And this diagram on the right side here shows all the different types of source mechanisms that we can have for gold mobility. But the one that we're going to focus on, and I'll focus on in this my PhD, is the metamorphic devolatilization model. And this is kind of a prominent model for gold mobility and gold sourcing, especially for Phanerozoic or modern day deposits, which are fairly rich in metasedimentary rocks, definitely more voluminous versus the Archean gold systems. So we're going to want to look at both the metasedimentary rocks and the volcanic rocks as potential source material. So essentially, the concept behind this is that when we regionally metamorphose a sedimentary rock or volcanic rock, the rock experience multiple water-releasing reactions along its prograde path. And especially focusing in on the green schist amphibole transition, which generally occurs between this 450 to 600 degrees Celsius temperature window. And so during that, we have the breakdown of chlorite to produce amphibole and mafic rocks. And then sedimentary rocks will see chlorite to produce garnet or biotite to produce staurolite, etc. And these H2O releasing reactions are continuous along its prograde path until it hits the solidus. And the key thing is that these reactions are typically coeval with the breakdown of pyrite to form pyrrhotite, and this does 2 things. It is able to release some free sulfur into the system, which under the right conditions can bond with the gold and allow it to be transported in the fluid. But it also can fully break down the pyrite and expose essentially the gold that is maybe trapped within the pyrite to the fluid source. So this model is kind of favorable because it kind of easily explains the requirements of synchronous deformation, of fluid flow, and gold leaching, all occurring around the same time and under the same conditions, really. So why is the Poetico subprovince then so important? Well, it's one of the 5 metasedimentary subprovinces in the Superior Craton. So these subprovinces are all Neo-Archean, about 2.7 billion years old. They share similar characteristics, and one of that characteristics is that they're typically overall higher grade higher metamorphic grade than their adjacent greenstone belts. And they contain these metapolitic and semipolitic mineral assemblages, which are quite sensitive to differing pressure temperature conditions, and can allow us to investigate the metamorphic evolution of these Neoarchean rocks. It's also one of the longest metasedimentary belts in the world, covering over 1,200 kilometers from the US to all the way to almost to Quebec. And so it gives us a chance to look at a long lateral variations along a major potential source area. And briefly mention that the metamorphic grade rapidly increases from the margins of these belts, from green schist to granulate facies in the center of the basins. Okay, so the two main objectives we want to answer with this is we want to test the devolatilization model for the Poetico metasediments and potentially any volcanic rocks associated with that. So would be looking at the timing of these prograde reactions, how they fit in with deformation events and gold deposition within the greenstone belts, what the composition of the fluids and the volumes of the fluids released during these prograde reactions, and investigate the potential of a metasedimentary versus a volcanic source. And then the second part of that is to identify variations within the Poetico subprovince, but also compare between the Pontiac and Poetico subprovinces. So comparing the metamorphic conditions that we see, comparing the differences in the basin composition, and that can kind of hopefully allow us to make a comparison between the well-endowed Pontiac and Abitibi system here versus the poorly endowed Poetico and Western Wabigoon or Wawa systems. So I mentioned in my title a quantitative PTTx approach. So what does that mean? For metamorphic petrologists, we're talking about the pressure temperature conditions very specifically. And so there's a few methods to try and obtain PT information. The one that will be able to get quantitative PT information is by combining phase equilibrium modeling and things such as mineral chemistry and petrography to quantify these mineral assemblages, the PT conditions of these mineral assemblages. Second part of it is the little t, the time. So that's where we can obtain absolute ages on geochronometers such as garnet and monazite, zircon, and titanite. And then the last part, the X, is the composition, and that's where we consider the open system behavior of metamorphic rocks, and looking at the whole rock chemistry changes, as well as doing some phase equilibrium modeling the composition. And yeah, so the main part of this presentation is going to be looking at the PT conditions, as this is something that kind of a brick that we need to sort out first before we tackle the full gold fluid window, is to really identify what the PT evolution of the Poetico is. So the first part of that is doing the transect mapping. So we spent time over the last 2 summers in the western and central parts of the Poetico subprovince, where we mapped about 600 outcrop stations. And so we have 5 different map areas where we have isograd information, structural relationships, contact relationships, and some idea of the stratigraphy of the basin. And so for the stratigraphy, again, as I briefly mentioned, we're dealing with mainly turbidite sequences, which are likely a kilometer thick, and have preserved, pretty well preserved primary structures. But this grades into magmatitic paragneiss in the central part of the subprovince. And what we've seen in the transect mapping is that typically estimated at 1 to 10% partial melting, with some zones getting up to 50, 60% partial melting of the sediments. We also observed mafic relatively thin mafic volcanic units that are generally interlayered with the sedimentary sequences. And these are pillowed flows and massive coherent units. And so just going a little bit more into that, for the sedimentary units, we divided into semi-peelite and peelite compositions. Samitic compositions are overall rare. So for semi-peelites, we're talking about 20 to 40% of aluminous minerals. Peelites, over 40% of aluminous minerals. And that's kind of important for talking about metamorphic assemblages. In terms of graphitic shales, they weren't observed in our transects, and iron formations as well. They're rarely observed. And one of the main things is that there's very little spatial variation in terms of the proportion of peelite to semi-peelite or anything else within the sedimentary units across the basin. For the volcanic units, it's somewhat a bit of a different story. It's up to 30 area%. But this is generally restricted to the biotite, garnet, and maybe staurolite zones. Once you get into the higher grades, there's no real mafic volcanic interlayers there. And you see this map here, I've shown actually the Beardmore Gelatin Belt, which is generally considered part of the Wabian subprovince. But what we're seeing is that there isn't any metamorphic discontinuity between the subprovince boundary, the Beardmore and the Quantitative, and that the isograds actually sometimes cross over these inferred subprovince boundaries. So when we're talking about a potential source area, we want to be thinking about these transitional basins as well. And we actually see this these transitional zones where we have up to 30% volcanic units occurs on both the northern and southern margins of the Poetico. So in the northern parts, these contacts tend to be sheared more. In the Beardmore Gelatin Belt, for instance, there's shear zones that separate these units. But in the southern parts, we can see that these are generally looked to be primary contacts between the mafic volcanics and sediments. Quickly on the intrusions, we have outcrop scale granite diorite and lamprophore dikes, which appear to be pre-tectonic and pre-metamorphic in nature. We have large scale monzonite, syenite plutons, similar to what Antoine described for the Pontiac. And then we have the leucogranitic dikes, which occur at regional and outcrop scale, and are partial melts of the Quetico sediments, typically found within the migmatite zone. So the metamorphic isograds specifically are chlorite, biotite, garnet, andalusite, staurolite, cordierite, silmonite, the melt, and orthopyroxene. Now, not all the transects show this full range of isograds, but especially the orthopyroxene isograd is only found in the eastern part of the easternmost transect that we mapped, and as well the melt zone is not found in the western transect. So overall, we see an eastern increase in metamorphic grade within the Quetico. The isograds are slightly generally discordant to the bedding, to the main foliation, and as well as structures. And I also wanted to point out that the chlorite, biotite, garnet, and staurolite, and silmonite are all along the typical Barovian gradient, but these andalusite and cordierite isograds typically don't fit with this gradient, this Barovian gradient. So it gives the potential that there could be two different gradients within the Quetico subprovince, but looking at the geometry of the gradients, they do seem to still be parallel to each other. In terms of the structural history, Williams in 1991 described 4 phases of deformation. We were able to see all of these different deformation events. The D1 structures were pretty rare, only found in the Beardmore Gelatin Belt. And then the S2 is the main foliation, that appears at low to medium grades. We can see that there's a slight rotation of S3 with generally 15 to 30 degrees versus S2. And then S4 is really restricted to shear zones and within the high grade migmatites. And one thing I want to mention is that the younging directions are dominantly towards the margins of the subprovince, both on the north and southern sides of the Poetico. So that kind of gives us the picture of an anticlinal basin geometry. So now just for the last part, I'm going to present some kind of early interpretations of PT evolution based on phase equilibria and petrography. So we're inferring here in two metamorphic events to describe the first one to describe the cordierite and andalusite assemblages that we see. Now, a lot of the previous work attributed these cordierite and andalusite assemblages to late isothermal decompression after a Barovian sequence or Barovian gradient. But what we actually see is that these cordierites are pre the main foliation, so pre D2 or even Syn D1. And these assemblages are actually overprinted by garnet and staurolite, etc. So this diagram that I calculated in theoretic domino for a metapelite shows that if the cordierite's field is around 2 to 4 kilobars and 600 to 700 degrees C in temperatures. You'll notice that I put the equilibrium assemblage here right on the garnet inline because at this point it looks like most of the garnet is after the cordierite, but it's potential that some of the garnet cores may have grown with the cordierite. And then the second event is late D2 to D3. And that's where we see the garnet staurolite assemblages and goes into sillimanite at higher temperatures. And this is broadly constricted to 5 to 7 kilobars and 550 to 650 degrees C. And the reason why why I've interpreted this as two metamorphic events instead of just one counterclockwise event is for two reasons. We have the relationship of chlorites to garnet. So that is not a reaction that would occur after this first equilibrium assemblage. This requires increasing temperatures at higher pressures. Similarly, we see the progressive growth of garnet after staurolite. And to get this progressive garnet growth, we need to be increasing temperatures at relatively higher pressures and at relatively higher pressures. So as a summary, we see a central and eastward increase in metamorphic grade. We have structure discordant isograds, and an overall appears to be an anticlinal basin geometry. We've identified some D2 andalusite and cordierite assemblages, which indicate an early low pressure, high temperature metamorphic event. And then we're going to test this hypothesis by looking at the mineral chemistry on garnet, cordierite, and chlorite, etc., and hopefully attain some uranium lead ages on accessory minerals and inclusions in cordierite and garnet. So thank you everyone.